Hello, my name is Ivan and I'm going to quickly present our paper Bias In, Bias Out, Finding Unbiased Subnetworks in Vanilla Models. So let's start with some context. So we know that neural networks they can perform very well on a variety of tasks. However, these models are also known to be prone to learning biases contained in their training data. And when I talk about biases, I'm specifically talking about spurious correlations. So let's consider, for example, the Celebi dataset, where in the training set, there is a natural correlation between the hair color and the perceived gender of the individuals. So if you train a neural network to predict the hair color, it may become biased, in the sense that it may over-rely on gender-related information. As a result, this model may perform poorly on samples where the spurious correlation does not hold. From this example, we can see that biases they can lead to technical limitations, as well as some ethical concerns, notably related to fairness. Therefore, debiasing is very important. However, model debiasing usually involves retraining all of the parameters of the model. But let's consider that you have an already trained model which you later discover that is biased. How can you correct it or debias it without having to update all of its parameters? More precisely, in this work, we are going to consider the following. So given a biased network, how can we extract from it an unbiased subnetwork without having to do retraining or fine-tuning and without relying on an unbiased training set? For that, we propose a method that we call bias invariant subnetwork extraction, or BIS. So we consider the setup of the biasing classification, where each input is associated with two labels, Y, which is the target, and B, which is the bias. And we assume that the training set is biased, in the sense that there is a high spurious correlation between those two labels, while the test set is considered to be unbiased. So the issue is that a trained network is likely to perform poorly on the unbiased test set. So our goal is to debias a vanilla trained model, specifically through structure pruning, which means by removing entire neurons or filters from the network. And we want to do this without fine-tuning and using a biased training set. How we do that? So given the vanilla trained network, we are going to freeze it and decompose it into an encoder and a classifier. And we want to prune the encoder in such a way that the representation that we have here is informative of the target at the same time that it is more invariant to the bias. And for that, we are going to learn a Boolean pruning mask. How we do this? So inside the encoder, we are going to associate each neuron or filter with a trainable masking parameter, MI. Then we are going to modify the output of each of these neurons or filters as follows. So for each output, we are going to multiply it by an indicator function that depends on the corresponding MI. And we can see that if MI is positive or 0, the corresponding output is kept, otherwise it is pruned. And these parameters MI, they are trained by minimizing a loss, where the first term is a reweighted cross-entropy loss, where we give more importance to the samples where the spurious correlation do not hold. And the second term of the loss aims to estimate the amount of bias information that can be extracted from the encoder. For that, we are going to use a linear probe that we train to predict the bias from the latent representation. And the goal is to minimize the multiple information between the predicted and the ground truth bias labels. And at the end, we are going to prune a neuron or filter in the encoder if the corresponding MI is negative. Regarding the experiments, here we show the results on Celebi. So we can see that the vanilla model has an accuracy on an unbiased test set of 76.5%. And if we prune this model using our method, we can improve the accuracy up to 90%, which is comparable with the best methods in the table. And if we allow some fine-tuning after pruning, we can improve the accuracy even more. And here we are pruning almost 70% of the weights, while considerably reducing the complexity during inference. But a natural question that arises is, what if we do not have access to the bias annotations? In that case, known as unsupervised debiasing, we are going to use pseudo-bias labels. To obtain these labels, we are going to use an identification model with the same architecture as the original model, but trained for only one epoch. And why? It's because we consider the assumption that bias is learned first. In that case, the identification model is supposed to be strongly biased. So we can use its predictions as our pseudo-bias labels. And in that case, we are still able to considerably improve the performance of the model on an unbiased test set. So we have proposed a method for debiasing through structure pruning without fine-tuning and without using unbiased training data. And the direction that we are proposing is that we can obtain bias-robust and fairer models via architectural interventions. So thank you very much for your attention and your interest. And if you are attending CVPR this year, please come talk with us during our poster presentation. Thank you.